Here we're continuing with 3D shapes or forms. So let's start out with a rectangular box. By the way, a rectangular box is also known as a rectangular prism. So rectangular prism. So that's the same thing as saying a rectangular box. All right, so I have drawn this box and it has, of course, 3 dimensions. So let's call this length, and why don't we call this width, and why don't we call this height? Now, you don't have to call them length, width, and height. You could call this depth, for instance. However you want to do it, it's totally fine. I'm going to use L for length, H for height, W for width. But if you have other letters that you want to use to represent these dimensions, that's totally fine. The idea is that the concept is being represented, and if you want to use your own terminology for these distances, that's totally fine. So you could use D for width, as in D for depth, instead of width for NW. That doesn't matter to me. Okay, so let's come up with the entire area that is just right here. So how would we come up with this area of, now it kind of looks like a square, but it doesn't necessarily need to be a square because maybe the length and the height are different. So let's just call this a rectangle. A square is a very special type of rectangle, but let's just call this a general rectangle. How would we find the area of this? You would multiply the length times the height. So the area so far is right here, length times height. So I'll say area is length times height, L times H. But if I want to find the area of the entire outside of this rectangular prism, this rectangular box, there's 6 faces to it. So this is one face. Can you imagine, though, even though you can't see it on the back, that there is another face that's identical to this one? There's a front and a back. So if I find the area of this, I automatically know the area of that because it has also an L for the length and the same height. So instead of saying L times H and just leaving it there, I'm going to have 2 of them. So I can write 2 times L times H, 2 times L times H. All right, then I need to add that to the top and the bottom, Now the top face and the bottom face, or the floor, they are identical rectangles to each other, just like the front and the back are identical rectangles to each other of those guys. So the floor and the ceiling, so to speak, are other rectangles. Now, what is the area of that rectangle? Well, this area would be the length times the width. All right, so we plus length times width. But remember, there's a ceiling as well that's identical. So mark that down for 2. Okay, and now, last but not least, we have this face, and then you could say the right-hand side of this box, and then on the other side, the left-hand side of that box on that other side. And those are identical rectangles as well to each other. And how do you find the area of just say the right side? Well, it has a width and the height. So that would be W times H. W times H. But again, there's 2 of them, so may as well put a 2 in there. So the area of the entire outside of this rectangular box is 2 times length times height plus 2 times length times width plus 2 times width times height. And there are a couple ways that you can rewrite this formula. The idea is to really understand where the formula comes from. It's not to memorize the formula, but it's being able to recreate the formula from your own understanding of how these 3D solids are created. So even though one person might use this formula, you can rearrange this formula and it's totally fine. As long as you understand how to get to this, you can come up with a different version of this formula, and that's totally fine. For instance, what if you wanted to move this over here and this over here? So for instance, the area, all of this could be equal to, you put this first, okay, plus this second, okay, plus maybe you'll do these guys the last. That's fine. Do you see that these formulas, this formula and this formula, are the exact same at the end of the day? They just might be a little rearranged, but they're the same thing. There's even more ways to make this look differently. For instance, do you see that every single one of these terms are being multiplied by 2's? Well, what you could do is you could extract the 2. You could factor that 2 out and put it on the outside of a parentheses, and then just put all of these guys in here without their 2's. Because 2 on the outside of a parentheses means that you need to distribute over everything inside. So whether you find out what the length times the height is and then multiply it by 2 right away, or whether you do the length times height, then you add that to the length times the width, then you add that to the width times the height, and then you get this full sum, and then at the very end, you double it, it comes up with the exact same way that any of these other formulas were. The idea is to not memorize the formula for the area of the outside of a box, but be able to construct it from the ground up organically, because you know all of the components that need to be added together. That is what I'm trying to get us to really get to. Instead of memorizing formulas, really understand where they come from. And a way for us to be aided in this way of really understanding where these formulas come from is to actually break this entire solid down so that it is ripped up into its component parts. What does that mean, and what does that look like? Okay, so let's take something that looks like this, but imagine that you have a cardboard box and that it is recycling day in your neighborhood. And so you're going to have to break down that cardboard box so it's flat so that it can fit into the recycling bin. So we've got something that looks just like what we had before. A rectangular prism or a rectangular box means the same thing, but we're gonna break it down, like take out our scissors and cut it so that it's into its component 2D shapes. This whole thing is a 3D shape, 3D rectangular prism, but let's break it down into its 2D shapes. It's got rectangles, and you can break them down and create what we call a net. So we're gonna break it down into a net. So let's just look at the our length times height times width. And again, you can use different letters if you want. All I'm doing is representing this horizontal distance, vertical distance, and depth distance. If you want to use other letters for it, you could even use XYZ, doesn't matter, as long as you know what you're talking about. Okay, so what we need to do is we need to draw this rectangle as it were cut out so we can put it into that recycling bin. So I'm going to write that rectangle right here, okay? And that rectangle has a length. I'm still using the same letters that I am in this 3D solid as to this 2D net that we're going to create. So this is the length, right? And this is the height. Okay, so we're done with that one. Now let's do the right-hand side. So that's the height and width, okay? So we still have over here, what we have is a width and a height. So we're gonna say something like height and width. All right. So this height is the same thing as this height. Do you see that this right-hand rectangle has the same height as this front rectangle? Because the height is the same all the way around the object. So this H is the exact same as that H. Now, we're not using L here. There's no L to speak of, but there is a W, so that's why I put a W here, okay? So that's the same thing for the other side, the left-hand side. So what we can do is bring this out here like that, and we'll have, again, this width is back here. If you could be Superman and see through this object, you would see that there's a same width back here as well. So I'm going to put a W to represent that width, and it's the same height. So right now we have taken care of 3 faces of this 1, 2, 3, 4, 5, 6 faced solid. So there's 6 faces to a cardboard box. And so we have written 3 of them flat, like we have cut them out for recycling day. Okay, we've got 3 more to go. So let's talk about the bottom right here. So this bottom has, and I'm going to run out of room, but this bottom here has a length and a width. So we're like deconstructing this. So we've got this length, which is this length right here, but then we've also had this width. So this width is this way. So I'll write W's here, like that. And I only have so much board. I would probably go down a little bit further if I could, but I'm running out of board space. That's okay. All right, so we have this bottom here, like that. I'll write this L a little bit smaller, like that. So we have this bottom part, and just like we have the bottom, we have the ceiling as well. So let's write that ceiling above it. And what would that ceiling look like? It would have a length. That's this length. This L corresponds to this L right here, and this W corresponds to this W right here, and that W over there. So that's a W over there, okay? Now can you kind of see, we're not done yet, but can you kind of see that you could fold this box up into not just a 2D shape, but into a real solid that you can hold. And you can kind of imagine that these are being pulled out from the board so you can actually reconstruct it. Okay, we've got 1, 2, 3, 4, 5. We need one more. There's one more. What did we forget? Well, remember this front face? There's also an identical face on the back as well. Okay, so I'm gonna run out of a little room, so I'm gonna erase the word net. And do you see how this back face is connected to this bottom, which is right here? So, or actually connected to the ceiling. This ceiling and bottom are the exact same in terms of the area. So, okay, so let's put one more here, and that will be this back part has a length and a height. Length and a height. Okay, so now we have gotten all of these component rectangles flat out. It's like we have broken this entire box down into just the areas of each specific rectangle. Now remember, there were 6 faces, but really only 3 distinct rectangles. And each distinct rectangle has its copy. So like the distinct rectangle on its front has its copy on the back. Distinct rectangle on the right has its copy on the left. The distinct floor has an identical ceiling. So why don't we, just for clarity's sake, call maybe this the front X and the back X. And then the right side we'll call Y. So the left side we'll call Y. And then the basement, so to speak, or the floor and the ceiling could be Z's. So you don't have to put like these X, Y, Z's in here. I'm just doing it right now to show you that these X's are identical rectangles. These Z's are identical rectangles. These Y's are identical rectangles. That was the reason why I did that. You don't have to do that on the quiz or anything. I'm just showing you that there are 6 faces, and each face has its counterpart that's exactly equal. So while there's 6 faces, there's really 3 pairs. You can think of it like that. Okay, so now we have our net. Now, why do we call it a net? It doesn't really look like a net right now, but when we start to draw in the implications, so let's actually use some real numbers here. So let's say that the length is 3 units, let's say the width is 5 units, and let's say the height is 4 units, okay? Let's just say that. So if the length was 3 units, that would mean that we've got 1, 2, 3, 1, 2, 3, 1, 2, 3. All right, you broke those into 3. Okay, let's say our height is 4. So that means that we're going to break down all of our heights into 4. So this would be 1, 2, 3, 4, and it goes all the way across like that. Okay. And let's see what we've got in terms of our width. Our width is 5. Okay, so that means that this rectangle needs to be broken up into 5 columns. 1, 2, 3, 4, 5. Okay, and this has a width of 5. 1, 2, 3, 1, 2, 3, 4, 5. All right. I'm trying to make them into the best squares that I can, but all of these little parts of the net, it's starting to look like a net, isn't it? Like if you cut a basketball net, all these are squares, or actual squares. Okay. And then this has a width. So, so let's see, our width is 5. So let's divide this into 5. 1, 2, 3, 4, 1, 2, 3, 4, 5. This has a width of 5. 1, 2, 3, 4, 5. Get 5 here. So there's 5 here. And then this is a height. The height is 4. So we'll do 1, 2, 3, 4. 1, 2, 3, 4. Good. Okay. So what we have done is we have created our net. And if you want to find out the surface of all of the areas put together, the surface area, so instead of just area of one rectangle, we're doing the area of all of the rectangles, which is why when we are talking about these solids that you can actually hold like this, instead of just calling it area, we call it surface area. All right, surface area, which you might see me abbreviate as S times A. I'm sorry. What I'm trying to say is this is the abbreviation for surface area, SA. Students often think that I am multiplying S times A. I am not multiplying S times A. This does not mean S times A. This just means surface area, okay? So this is just an abbreviation, so I don't need to keep writing out surface area over and over and over. All right, so SA, surface area. The way that I could find the surface area is write the net out, which we did, and count all of the squares. Every single little square in here is truly a square, 1 unit by 1 unit square. If I had said 3 centimeters by 5 centimeters by 4 centimeters, then each of these squares in here would be centimeter by centimeter squares. Centimeter, a square centimeters, okay? If I said this was inches, all these would be square, little square inches in here. I know they don't look exactly like squares because I was freehanding it, but each of these are really a square. Each dimension to the right and to the dimension up is the same exact amount. Just 1 centimeter by 1 centimeter, 1 inch by 1 inch, 1 unit by 1 unit. Okay, so if I counted all of these squares in here, I would come up with the surface area of this rectangular prism. So this is a really good tool because it shows exactly what's happening. And on the quiz and test, you'll have to write your own net. So when we say take the object and write a net of it, this is what that is saying, okay? Now your net might look differently than my net. As long as you have all 6 faces, that's fine. But maybe if you wrote your net, you would have put this connected, maybe down here, or this, there are different ways that you can connect these, and that's totally fine. So it doesn't need to be in this exact form. You might have the ceiling on, down here and the floor over here, but they all do need to be connected. However you feel, if you were breaking down the box for recycling, how would you break it down? And now you can see that you can fold it all up back into its original solid. Okay, so this is what a net is. And we will continue with surface area in the next video. We will create nets for not just rectangular prisms, but all kinds of other shapes as well. See ya.